This is a detailed look at the project's software. We start from Arduino IDE and the codes written for both the Bluetooth controlled car and the station's sensors. Both codes include the function sendData. This function enables each code to send the data it needs to a Google Sheets file online. This is achieved through a JSON code, a JavaScript code added in the AppScript extension in Google Sheets. The sheet is programmed to write the number of readings in column A and write the readings date and time in the next two columns B and C. The charger's status are added in columns D and G. The total number of cars is written in column E, and the total energy consumption is in column F. For developing the application, we aim to use the APIs offered by Google Cloud. Sheet API is used by our Flutter code with JavaScript decoding to attain the data from the sheets to the app. To start with Flutter, we open the pubspec file. Here we have libraries and extensions used such as GSheets for Sheets API, HTTP to access the web, Google Maps Flutter that enables us to use maps offered by Google, Flutter local notifications to send notifications to the user, and the credit card library used in payment methods. The first step is to retrieve the data from Google Sheets. In data fields and battery fields files, variables are created in the same number as the data in Google Sheets. The app, of course, decodes the JavaScript language in the AppScript and retrieves the information from the sheet. The following is datasheets API.dart. This file includes the credentials for the Google Cloud Key. It enables the use of APIs offered by the cloud. Here you can find the links for each sheet of the 3 sheets in our project. Scrolling through the main.dart file, we see initializations of data fields and battery fields files for stations A and B, and also the car's battery. Most of the widgets in this project are stateful widgets, which help with user interaction instead of just a stateless widget. Lastly, in the main file, the project is redirected to main project page class. In the main project page file, the app is divided into 4 main pages: home page, maps page, charging page, and account page. In the home page, we include the percent indicator library along with battery fields files and data fields files too. The main function is called getUsers. Once the battery level sheet is read in the first line with getBatteryAll function, a for loop is made to get the last battery reading. Calculations are then made to calculate the needed kilowatt hour to achieve 100% charge. Then this amount is multiplied by DC and AC charging fares, and the prices are displayed for the user on the screen. In this section, a timer is placed inside the initState function that lets the page refresh each 15 seconds. If the battery level reaches 100%, the user is notified to disconnect charger. If battery level reaches 20%, user is notified to go to the nearest station. For the widgets, the screen is on standby until the battery sheet is read. For levels higher than 20% and lower than 100, the battery indicator color is green. Lower than 20 makes the color red. Reaching 100% adds the text battery full. The maps page is built using the location page, in which Sheets API is added along with the geolocator package. The Maps API key is also added to integrate our app with Google Maps. Then the stations, longitudes and latitudes are added to specify their map position. The locations are relocations inside the faculty's campus. The camera positions are also adjusted to focus on the locations instead of the whole map. In the getCurrentLocation function, the current location of the user is retrieved and viewed on the map. A timer is set for 5 seconds as the app is notified with updates for user location. In this project, there are 2 stations. Each of them is added in a Google Map function, so the user opens them with ease using the initialized camera positions. Marker IDs and pins are added to make the destination points unique in shape. Lastly, the location class has detailed stations info such as names, exact locations, and pictures. The hardware.dart file is considered to be the most important in the app. It's the charging page that compares between 2 charging stations. Here we have variables initializations like the car's waiting and car's charging, and also the waiting time. The app banner class represents the cars sliding to the left and right. Also here the locations for station A and B are initialized. In the getCurrentPosition function, the Haver-Sign formula is used. It calculates the shortest distance between 2 points on a sphere, such as the Earth. The distance of the current location is compared to station A and B, and the result is an approximated distance in kilometers. The app banner list for each station includes 5 different sliding cards that have very important information to the user, such as distance to station, battery reliability, number of cars charging and number of cars waiting, and the waiting time in each station. Like the home page, the main function here is getUsers, in which the data from station is retrieved and calculated, like the number of cars charging and waiting. If conditions are made also to display approximate waiting times for each range of energy consumptions. This is done for each station. In the function setState, the cards list is added for faster app performance and data retrieval. The timer updates the data on the app each 7 seconds for the stations. In the widgets section, there are different if conditions as follows. If the battery's reliability in kilometers is more than the station distance or equal, an extra condition is added to compare between the waiting time of the 2 stations and recommend the user the station with the least waiting time. The other conditions check between the battery's distance limit and the station's distance to see if a station's distance will not be covered by the battery. Then the car can head to the station that it can reach. The final page is the account page, including 4 text controllers that enable the user to add his username, email, password, and vehicle model. Once the user signs up, he is directed to login page, where the info he wrote appears in front of him along with the payment methods. Payment methods can be clicked to redirect the user to payment methods page where he chooses his preferred payment method. The credit card page is powered by a credit card package that lets the user add his card information and lastly validate his card. Next, we are going to discuss the hardware part. For the first section, we are going to dissect the connections behind the robot car. The robot car is controlled through an application called Bluetooth RC Car. The application connects to the car through the Bluetooth module connected to the Arduino. In the robot car design, we used AVR microcontrollers such as Arduino Uno and Atmega32. Arduino Uno was chosen for its abundance of libraries and rapid prototyping, while Atmega32 has a lower cost and has more optimization and customization. The H-bridge motor driver is connected to the Arduino's input-output pins. Through the Arduino code and the H-bridge, the motor speeds are adjusted. The speed of a DC motor can be regulated by adjusting the input voltage, with one of the most prevalent techniques being the use of a pulse width modulation. Pulse width modulation involves modulating the average voltage delivered to an electronic device by rapidly toggling the power on and off. A battery holder is added on the body of the car as a power source. Each battery is around 3.7 volts and the total supply reaches 11 volts. The battery holder powers the H-bridge and is connected to the voltage divider circuit. The Bluetooth module is connected to the Arduino's universal asynchronous receiver transmitter pins. Numerous Android applications are readily available, simplifying the integration process. Operating at a baud rate of 9600 through the UART, the module easily interfaces with any UART supporting microcontroller like Arduino Uno. A voltage divider circuit is connected to a Wi-Fi module on the ADC pin. The circuit is designed to measure the car's battery, then send the data to the Wi-Fi module. The Wi-Fi module then is coded by Arduino IDE to send the battery percentage to the cloud and keep updating the data each 10 seconds. To operate the ultrasonic modules, we initiate the process by utilizing the input-output triggers with a high-level signal, lasting at least 10 microseconds. Subsequently, the module autonomously transmits 8 pulses at a frequency of 40 kHz, then assesses the presence of a pulse signal returning. Upon receiving the signal back, the module generates a high-level output, and the duration of this high output on the input-output pins corresponds to the time it takes for the ultrasonic waves to travel to the object and back. Basically, what this means is that the distance is determined based on the time it takes for the ultrasonic sensors to send a signal and see an object and then receive a signal back. In the project, 2 of the sensors are placed to count the cars coming in and out of the station, and the other 2 sensors check the charger's status. The station's circuit is encapsulated inside rectangular-shaped laser-cut foam sheets and covered by acrylic transparent glass. This glass allows for easy error tracking and process optimization. Each station's rectangular cut part is connected to laser cut ramps that ease the process of the car going into and leaving the station.
Now it's time to test the integration of all these elements together. Test case 1 is exactly the same as the Google Sheets case. One car enters the station and is in waiting mode. Moves up to the charger and the app adds it to the number of cars charging. As it leaves the station, cars waiting and cars charging are changed to 0. Test case 2 is a case between station A and station B, checking if the app will respond correctly to the sensor's output. Both stations have 2 cars charging, but station A has 3 cars waiting and station B has only 1 car waiting. Test case 3. This case sees both stations at full capacity. Station A has only 1 car waiting this time, while station B has 5 cars waiting.
The following message is from both teams working on this project.